Good afternoon. Welcome to this session now. We have two talks in this session and then we break and have public talk after that. Our first speaker is Alessandro Bettini, and his title of talk is there. He will probably speak for 1 hour and 30 minutes and then we will have second talk. Please.
Okay. Thank you for the invitation. Yeah, I was here, I don't remember when, 10 years ago probably, and it was when I know the thing started. So the title that I gave to this conference, this lecture is if neutrinos are object spinors that are completely neutral. So what is a completely neutral particle? You know several of them, but all of them are bosons. The gamma or the Z, the H, the pi 0, the eta are completely neutral. It means that all their charges are 0 and they are equal to their antiparticles. Can be are any fermions that can be completely neutral? Neutrinos might be completely neutral, and neutralinos too, because neutralino is the counterpart of Higgs and some of these friends that are all neutrals. So electric charge, color, lepton number, and baryon number should be 0. This possibility, there is a difference. You can have a boson that is, or a meson that is neutral both if it's massless and if it has got mass. If you want to cook a fermion that is completely neutral, it must be massive. You cannot do that with a massless one. This question was raised many years ago in 1937 by Majorana, and Majorana fermions are only two components, one for each of the spin orientation, for example. Majorana put in this question, notice this was noted by Bruno Comtecorvo later on, put in the question of complete neutrality, implicitly introduced the notation of charge different from the electric one. Notice that only 12 years ago, after the baryon number was created or hypothesized, and in 53 the lepton number. Majorana did not know in the 37 clearly that the parity is violated in weak interaction, maximally in the charged current, and the flow lepton numbers are not conserved. By the way, the neutrino did not exist yet, it was not yet even discovered. So this is, let me start with some historical recollection. This is the famous paper of Majorana on the Nuovo Cimento is written in Italian, but is translated in English by Luciano Maiani and by others too. And he writes in the summary, we show that it's possible to achieve a complete formal symmetrization in the electron and positron quantum theory by means of a new quantization process. This is symmetric theory of electron and positron, because Dirac started with an asymmetric theory, but then the Dirac theory of course is symmetric, but with this funny hypothesis of the holes in the sea of electrons. The meaning of the Dirac equation is somewhat modified. It is no more necessary to speak of negative energy states, nor to assume for any other type of particle, especially neutral one, the existence of antiparticle corresponding to the holes in the energy. He did not like aesthetically this asymmetry in the starting point. The interpretation of the so-called negative energy states proposed by Dirac in 24 leads, as it is well known, to a substantially symmetric description of electron and positron. But he is not happy of that, and let's start from the beginning and let's try to make a theory that is symmetrical since the beginning, and he does that. From this new way, we can expect only a formal progress for electron and positron, but it looks to us important in view of possible extensions that the notion itself for negative energy states is abandoned. Indeed, we shall see that it is perfectly possible to build in the most natural way a theory of neutral elementary particles without negative states. The new approach allows not only to give a symmetric form to electron-positron theory, but also to build a substantial novel theory of the particles deprived of electric charge, neutrons and hypothetical neutrinos. it is probably, he said, not yet possible to ask to the experience to decide between the two theories and the simple extension of the Dirac equation of the neutral particles. Up to now we did not succeed, but we are trying. The same year, a few weeks later, Dirac, that was in Rome too, those times, in a paper on the symmetry between particles and antiparticles, writes the Majorana theory maybe in a simplified fashions, and he finds that if neutrinos obey Dirac equation, Majorana did not give any hint on how experimentally distinguish between the two cases. Neutrino, Racah did it just a few weeks after. Neutrinos emitted in beta minus decay, like this one on a nucleus, can induce only by beta plus process and vice versa if neutrinos are Majorana, are Dirac. But if they obey Majorana equation, any neutrino can produce both electron and positron. So this neutrino here that we know now that is an antineutrino, if it is Dirac, going to another nucleus can produce not only a positron, but in some cases also an electron. Neutrons, he observed also that neutrons can obey Majorana equation for two reasons. One, that they have magnetic moment, and they are, so they cannot be of the two signs, and also that if they were, neutron would decay beta minus into protons, and beta plus into antiprotons with equal probability. This second observation was not really taken by Potacorvo, for example, that made the hypothesis of neutron-antineutron oscillations. To remain on the final step on the historical recollections, 1 year, 2 years later, it was Fari that in this paper, this time on physical review letters, physical review, it was only physical review, those time, the two nuclei of, if you take to the two things happening in the same nucleus, then you have the double beta decay process. The neutrino does not go to a neutron in another nucleus, but inside the same nucleus and becomes a propagator in some sense. He says the double beta decay with two neutrinos were already been theoretically known, and he claims, hopes at least, that if the Majorana theory only two particles, the electron and positron, have to be emitted, and the transition probability is much larger. Unfortunately, that is not true. It's much smaller. Now, just here is just to recollect you now to the physics. You have already seen a couple of times this mixing matrix. That is the rotation through the three Euler angle between the eigenstate of the mass, or simply eigenstates, because they are the eigenstates, and the flavor. This is the spectrum, and as you know, we don't know, you have already this morning, we don't know the absolute scale, the sign of delta m squared, and the phases. This just give you, was asked this morning, the uncertainties of the angles and on the masses. This is a recent fit of the group of Bari. Here they plot the number of standard deviation from the minimum point of the chi-square, fitting all the data together, and you see that the delta m square, I measured them in milli-electron volt squared, is known within 2-3%, the both of them. Of the smaller one, you know also the sign, of the larger one only the absolute value, because the phenomenon of oscillation is independent of the absolute of the sign, but the matter effect are. And the signs, the three angles, are known within a few 5%. The latest one, the smaller one, is 10%. You see the minimum here, the two curves are for inverted, normal and inverted hierarchy. There are the tendency of having two minima, not at the maximal mixing at 0.5, but a little bit one on the side, one on the other side, but still the maximal mixing is possible within 1 sigma or 2 sigma, depending on the hierarchy. So it's not excluded yet, but it's not the best, the point of the best fit. Now let's go to, I will be a little bit elementary, to the Dirac, to recall you the Dirac equation. The Dirac equation, the bispinor of Dirac has 4 components. We have 2 spinor, one describing the particle, the other the antiparticle, and the 2 components are the spin orientation. For example, if the particle is not at rest, you can use the helicity to distinguish between the 2, the eigenvalue of the. Notice that helicity is a property of the 2 component spinors, not of the 4 component spinor. I tell that because there is a lot of confusion in the literature between chirality and helicity. Chirality is another thing. Is a property of the 4 component spinor and is eigenvalue of the gamma 5 matrix. It's obtained by a spinor with those projectors. 1 minus gamma 5 gives you the left chirality, and 1 plus gamma 5 the right one. These 2 are eigenstate of the chirality with the eigenvalue minus 1 and plus 1. The conjugates are these things here, and notice that in the mass term in the Lagrangian does not commute with the chirality, so chirality is not conserved, not even by the free motion of a particle. Now, what is the difference with helicity? If I take, for example, the left, I call left the negative chirality. That is different from negative helicity. But in literature, the term is used for both. So if I take the left 4 component spinor, this is the Dirac equation for it. You see that only one of the 2 spinor or 2 components appear in the 4 component left one and similar in the right one. These are the equations that are, you see, coupled. You have chi both here and here, phi both here and here. If you take out the helicity content, for example, of the left one, you make a small calculation, you find Z is the direction of the motion, and you find this expression. And so there are both components with plus helicities and with minus helicity. If they are ultra-relativistic and the energy is much larger than the mass, then you can simplify it like that, and you see that is predominantly negative helicity, but there is a small component proportional to m over e of positive chirality. For electrons emitted in a beta decay with a large Q value, this component might be sizable. Now, what is Majorana equation? The question in modern terms posed by Majorana is the following. Is it possible to find a spinor, 2-component spinor, constructed with the components of the phi only, and hence without any extra degree of freedom, which transforms like a chi instead of a phi, and consequently can take its place in the Dirac equation, and similarity for the chi? The answer is this. This phi, big phi spinor is I times sigma 2 times the conjugate of the chi. And similarly for this, and I for sigma 2 is this matrix. So if you put in the Dirac equation, you find this equation here for chi and for phi. And you see the 2 equations become decoupled. Also being decoupled, the mass term here might be different. You might have 2 different masses here. If the mass is 0, the 2 equations are equal. So there is no distinction between Majorana and Dirac equation if they are massless. So when you talk of Majorana particles, you will always talk of a massive particle. However, the particles that you know, the spinors you know, all of them have a mass. On the contrary, in the standard model, it is assumed that neutrino has no mass, but this is contrary to nature. Now, Okay, this is about the exercise that we can go quickly or you can look after. If you take the charge conjugate of a Dirac or Majorana spinor, you make this simple exercise itself. So Majorana particles or neutrinos give lepton number by relation. If you have Majorana neutrino, the lepton number is violated. This happens via the mass term that maybe I will tell, but not too much. This morning you have more than I can tell now in the Lagrangian. There is no contradiction that we will see of this experiment. It's not true that the conservation of lepton number is proven by the experiment. It's not, because the character V minus A of the current. Let's have a look at the difference between the various possibilities. The neutrinos of the standard model, if you have a massive Dirac neutrinos, then we have seen just a couple of transparencies ago that the left neutrino has a component, a predominant component of negative helicity, and a wrong, let's say, helicity component with an amplitude m over e. That for energies of the order of GV, it is very small indeed, but 10 to the minus 10, let's say. The antineutrino that is still left has a predominant component positive of helicity and a small one, m over e, of negative. The difference between Dirac and Majorana neutrinos is in this number, in this small component, because if they are Dirac, when they hit the nucleus or something, they produce negative leptons, an electron or a muon, negative muon, not an anti-electron or an anti-muon. And this small component, both components, including the small one, make a positron or positive muons. The so-called neutrinos of Majorana has the same situation with as the helicity is concerned. But the small components of wrong helicity, in the case it is Majorana, makes positron, the one of the electron, of the neutrino, and the one of the so-called neutrinos makes electrons. So what distinguishes making electrons or positrons for a Majorana particle is the helicity. So if a neutrino is born as a neutrino by the weak interaction, it makes a positron only in a very tiny fraction of the time, this quantity squared. So it's not, and that was Raka who was proposing, but the probability that to happen is 10 to the minus 20 or something like that. So cannot be in practice observed. And vice versa for the positron. So Dirac neutrino and antineutrino are distinguished by lepton number, and if ultra-relativistic, as is the case in the laboratory and also in the atmospheric or solar neutrinos, practically always they are distinguished by helicity. If lepton number is not conserved, Majorana neutrino and antineutrino distinguished by helicity. Negative chirality neutrinos have this m over e component of antineutrinos, let's say. I don't know if I have the time for this puzzle, maybe not. Helicity is frame dependent. So one might ask, okay, if I am in this frame, this is neutrino, if it is Majorana, but if for another observer going faster than the velocity of this frame, the velocity will invert and it will become an antineutrino. So hitting a nucleus, the first one in one frame will produce electrons, in the other frame positron. Of course cannot be. It cannot be because what matters is the relative velocity between the neutrino and the target, and that is frame independent. Or, and that's you can find in a paper by Boris Kaiser, explicit calculation, because the interaction probability amplitude is given by the product of two currents, one for the lepton and one for the target. And these two currents change if you change the frame, but not the product that is a scalar. going quickly, I have to go quickly to the CSO, to the neutrino mass, just to, this is how the standard model gives the mass to the fermions. But for doing that, you need both the left and the right. And as Andrea told this morning, neutrino miss the right component. So you cannot, the standard model does not give the mass to the neutrinos. You can introduce right neutrinos, but in this case you have a coupling for them. It has been already told that is related to the vacuum expectation value will be as small as 10 to the minus 12 rotation. That is a number in any case. Another possibility is that neutrinos are Majorana, and then you can give, no, it was the next thing. You can build a mass term of this because neutrinos and antineutrinos are, the conjugate of neutrino is neutrino itself, and you can build something like that with the left and also with the right Majorana neutrinos. In any case, it was explained this morning, you get rather naturally to an expression like that, that is the seesaw mechanism, in which the neutrino mass is proportional to usual mass, for example, the one of the quarks or the leptons, and divided by the mass of the right Majorana. So a very big Majorana mass with a normal mass of the bottom or the top, whatever, will give you naturally a very small mass for neutrinos. Let's go now to the beta decay. The double beta decay with two neutrinos is a process, standard model allowed process, second order in weak interaction, that is completely legal. This is the graph. It happens for the double beta, for the double even nuclei, in which the transition to the nearby is forbidden. Xenon 136 can not decay in cesium, beta decay in cesium, because the ground state is higher, so it has to decay to the next one, to barium, and for that it has to emit 2 beta, not 1, and similar on the other side of the parabola for the beta plus. At the nuclear level, you have this transition, so 2 electrons and 2 antineutrinos, 2 neutrons goes into protons, and at the quark level you have this thing. This lifetime exists, has been measured, are very long, between 10 to 19 and 10 to 21 years, but they have been measured. Instead, you might have, if neutrino is a Majorana particles, it can become exchanged between the two and appears in some way like neutrino here and antineutrino there. I asked Boris to explain me something here. What is going in the propagator? What is that? This is a coherent superposition of eigenstates, of mass eigenstates. So it's a sum of the new E's, where new I's where the I identify the flavor, but not only, because this neutrino, if it is Majorana, has both characters of lepton number plus and lepton number minus. So when it is a superposition also of the two, plus and minus lepton number, plus and minus helicity, if you want. At one vertex is emitted with that combination that I showed before, and you have to pick up a probability that is the mixing matrix element, and here there is again another mixing matrix element, but it has to appear here with the wrong helicity, so you pick up the amplitude of the probabilities M over A. So then you sum coherently, and you have to sum, you find something of this type, where you have the square of the matrix element and this is the matrix element. This term is called the Majorana effective mass with the 3 masses. But when you go to this has implicit a m over e factor. This is a matrix element, but in decay lifetime, you have this m over e squared. This combination, you see that the Majorana phases appear in this combination. So the sum might, by this term might be negative, so you might have cancellation. If you want graphically, you plot these three terms in this graph. I put one, this is roughly 0.7, the first thing, time m1, time this one that is in absolute value 0.3 m2, time a phase that you don't know. And this again, you don't know the phase. So you put these three things together, and then you have ME. But you see that can become as small as zero in certain conditions, depending on the sign of the delta m squared. If delta, the big delta m squared is negative, so-called inverted hierarchy, you have this as a function of the lightest neutrino mass. This ME in electron volt is given by this thing, where the uncertainty, the blue band, is due only to the phases, phase on knowledge. The uncertainty on the parameter is only this small part here. So that's, if you increase the precision in measuring the parameter, that is important, of course, the angle, the mixing angle, you don't, here you don't gain enough. In the case of the normal hierarchy, is even worse, because you have this funnel that goes down and might go down to zero. So ME might be zero even if neutrinos are Majorana. But it's certainly if it is different from zero, they are Majorana. The half-life is given by the factor of three things. This ME squared that I want to measure, the nuclear matrix element, because this process happens in the nucleus, and the phase factor. The phase factor is not too difficult to calculate, but the matrix elements are. So what is the problem of the calculation? You have to go from here to here, and you have a nucleus of intermediate Z, so you have to calculate all the structure of the initial and the final state, and all intermediate states. For that you have to adopt some approximation. There are three of them practically: this quasi-particle random phase approximation, the shell model, and the interacting boson models. This gives results that are not very different from one to the other, and you can have some information, but not too much, from the two neutrino double beta, where a calculator you compare with the measurements, because notice that the momentum transfer in the two cases is much different. Because in one case you have to emit two neutrinos, you do not. And there are other reasons of uncertainty. In any case, you see here are three calculations. Two of them, the QRPA and interacting boson model, agree rather well. The shell model is down by a factor of 2. So these things are known within a factor of 2 or 3. As already told you this morning, Boris. So let's go here to the sensitivity of the experiments. What you measure is the sum of the energy of the two electrons. If for the double beta decay with two neutrinos, you have a continuous spectrum like that. If you don't have the two neutrinos emitted, then you have a line at the energy of the difference of the Q value of the transition that you know very well. So you are looking for a peak here in a position where you know this is the ratio between the sum energy, kinetic energy of the electron and the so-called Q beta beta, that is the Q value of the transition. Now, the sensitivity of the mass is inversely proportional to the the Majorana mass to the inverse square root of the lifetime. So if you are in presence of background, the lifetime, the sensitivity to lifetime goes as the square root of the background, inversely of the background. And to the mass then with the fourth root. So you have this rule of the thumb that the sensitivity to the Majorana mass goes to as the exposure, the mass of your isotope times the time of exposure, the background index, and the refraction index. So you see from here that you want to increase by a factor 10, for example, my sensitivity, and I don't act on the background. I have to multiply my sensitive mass by a factor of 10,000. That, of course, is impossible. If, on the other hand, if I want to reduce the background to 0 or almost to 0, then the dependence will be proportional to the square of the exposure, square root of the exposure. Notice also that a background that is here is not this plot, this graph is not faithful, because up to that, in addition to that, you have the background due to other sources. But if you eliminate all the background, you still have in this, where you have the line here, the tail of the double beta with 2 neutrinos. And the only handle against that is the energy resolution. So what are the background? The background are everything is background, and background is everywhere. Cosmic rays are a background. And you go for fight this possibility, this enemy, you go underground. There must be a laboratory, not a cavity. That means that you have to have all the services, the power, the measurement of the background radiation, etc. Natural relativity. Natural relativity is everywhere in the environment. For that you have to calculate, measure the environment, gammas, neutrons, and build the shielding that is needed. In the shielding itself you have radioactivity, and you have to calculate with a Monte Carlo, whatever, the maximum tolerable contamination of any of the species that you might have there, and also screen all the components to check with the germanium counters, for example, if they are within the specification. In the electronics, so the readout that is near to the detector. So if you put there a wrong capacitor, even if the capacitor has a dimension of a tenth of a millimeters, can destroy completely your experiment. Surface contamination. Surfaces are terrible because powder contains thorium and uranium, so you have to minimize surface over volume ratio. Cosmogenic metastable. The cosmic itself, they have high energy, but they can, by spallation, break a nucleus, and this nucleus, the daughters of the broken nucleus might have rather long lifetimes. If are short lifetime, you can make an anti-coincidence, but they decay after 2 hours, so that is more difficult. For that, you have to go deeper, and is more important in general this background for heavier elements. 2 neutrinos, like I said, the only weapon against this background is the energy resolution. And it's very important because if you take this, there is a parametrization by Primakov and Peter Rosen of the energy distribution of this curve that is given by this complicated formula, but near the end point, this is you can approximate the formula like that, that is the q beta beta minus the distance from the endpoint at the 5th power. Now, the fraction of double beta with 2 neutrinos in your energy resolution is given by this fraction, is the delta E to the 6th power divided by q beta beta at the 5th. So and the ratio between sigma and background so depends on the 6th power of the energy resolution. So the energy resolution and the background are completely critical. Now, what is to have numbers? I take 3 examples. So these are 3 of the running experiments. There is a running experiment with enriched germanium that is called GERDA at Gran Sasso, one with natural tellurium oxide that is called Cuore, that is being built at Gran Sasso, and two with Richard Xenon, one in WIP in America, that is EXO, I will tell something, and Kamlan Zen in Japan. Look, if ME is 500 millielectron volt here, you expect in 1 ton, 1 year, 400 events here, 250, 430, similar numbers. If it goes down to 50 millielectron volt, that means the inverted hierarchy is between 50 and 12. So you see 50, you are just here. You have 4 events, 2 and 4, so very few events. So this is below the limit of the present experiments. To go to 15 millielectron volt is just a fraction of the event. So where the status of the art is that in the past generation, the best experiment had a background figure of, that was either the Moscow experiments or 10 to the minus 1. The present generation of experiment aims to go to 10 to the minus 2, 10 to the minus 3. That means 10 times, 10 events in this scale, so they are sensitive more or less there. These are I'll go to the experiments now. These are, the green one are the approved and funded experiment. This is another experiment, Super NEMO, that is being designed and then tested. And there are several others, but I will stick on that. These are the parameters. The Cuore, as I said, is on tellurium. The active isotope is under 30, but this, in the natural tellurium, the double beta active isotope the fraction is rather high, it's 34%. So they use natural, not enriched tellurium for this reason. They have 1 ton mass in total. That means 200 kilos of the isotope. They use bolometers. They have I tell you more. The resolution of the bolometer is good, and the background index that they will have around 90. GERDA has 2 phases. The first phase is running, with half this mass. At the end would be about 4 kilos. Ionization, the background index, the energy resolution is better. This is full width half maximum. The background index is now 20. This is measured. The red one are the measured one. And the next phase is going to 1 in 10 to the minus 3. EXO is running, and they have a very good background index. The energy resolution is not so good, but is what you can do with a TPC, liquid TPC. SNOW Plus is in program. They will have a rather weak energy resolution, and they hope for this background. I skipped Kamlan Zen, that has a rather bad energy resolution, but and not so good background. Then we'll talk about next. This is a program at Canfranc with a gas TPC that aims for a very low background index and below 1% full width at maximum energy resolution at 2 MeV. I will tell you how. And then Majorana, that again, germanium diodes, that is under construction and will run in the underground laboratory in South Dakota. Super NEMO is an idea to have the laboratory, an evolution of NEMO. They need a very big hole that has been approved to be digged in the Botan laboratory nowadays. So they had to dig the cavity and then. Now, SNOW Plus is the dissolving neodymium in liquid scintillator. I will come to that. Now, just to classify the events, in principle you can do things to have the source equal to the calorimeter, like in the bolometer or in the germanium diodes, and you measure the energy. You don't have information on the tracks. Or you have a foil as a source. You can must be narrow because the sink has 1 MeV energy, so they have to go out of the foil, and you have detector on two sides. Here you have tracking and pattern recognition, but without the energy resolution. The energy resolution must be very good, like in GERDA, Majorana with the germanium, or quarry with bolometers. Modest, like with Exxon, that is a liquid xenon TPC, or also bad energy resolution, like in Kamala Z, there is no plus. Next, this idea of next is aiming to have both, measuring both the total energy and having a very good energy resolution, and also to have pattern recognition of the tracks with the gas TPC. Now, going down to the experimental results, there is all the experimental results but one didn't find anything. There is one experiment that pretends to have found something. That is the Heidelberg Moscow experiment. They had 72 kilo years of enriched germanium with the best background index in the world, 0.1. They ran 8 years with a very good energy resolution, this integrated over 8 years, and they find the spectrum around where they expect the signal. They expect the signal more or less here, and they find this line. They did find a few 4 of this line, but they don't identify this line here. And if you enlarge this figure, you have more lines that are not identified. If this is true, this is the lifetime, and depending on the matrix element, you expect a neutrino mass between 150 and 500 millielectron volt. But another problem is that the background here depends on where you fit the constant background. If you increase this window, the background will go up. So the significant that is claimed to be 4 sigma goes down to 2 sigma. Frankly speaking, to me, to the fit that I do, if I assume that is nothing, that is the zero hypothesis, and I go there, the difference is 2 sigma only. Also, the line is not exactly where, you see how well we know the position. The position is known to a small fraction of a kV, and they are off by 2 sigma. 2 sigma may be a statistical fluctuation. Okay. A similar experiment that is IJEX with a little smaller exposure do not find anything. Now, what are the experiments that are running now or being prepared? This CUORICINO means small cuore in Italian, and was a prototype of cuore that ran for several years. The idea here of the bolometer is the following. You operate at a few millikelvin, and you have a superconductor there. If this is a crystal, 5 centimeter, a cube of 5 centimeters, and if you have an Ennis deposit by the double beta decay or anything, you have an increase in temperature, and you go, to low temperature, because you remember that the heat capacity is proportional to the cube of the temperature. This is the Dubai temperature, of course. So if you go down the heat capacity, a small release of energy gives you an increase, appreciable increase of the temperature. You have a thermal sensor that is connected with thermal bath, and you see the pulse. They made 1 tower of these things. Each tower is 4 5 centimeter crystals with an energy resolution of 8 kV. And they ran 5 years, and they had this background index, 0.18. If they normally give the background index in kilo of the detector, but here is tellurium only 30% or even less than 30% because of the oxygen is the isotope. So if you go to the isotope, 0.65. Now, this is just to tell you, this is the principle also of cuore, that cuore is the big experiment that are now being built. They will have almost 1,000 of detectors, very similar to the other ones, for a total of 200 kilos with an energy resolution full width that I hope they are close to 5 kV, and the background index this structure, they are in the vacuum, the crystals, and they are taken in by a structure of copper that is ultra pure copper, but still the background is dominated by the surface contamination of the copper that takes between the copper that takes the crystals and the crystal, you can vacuum, not a liquid or something. So the alphas can fly and gives you, if they release part of their few MeV energy, only part of that you see, that gives you something that is near to the signal. So they have to build a number of these towers, similar to those of the CUORICINO, put in the cryostat that has to go to a few millikelvin. The cryostat is built, they are now making a long process to clean the surfaces. The crystal has been produced in Shanghai and they are cleaning off. So they are working on that, and they aim to this background index that is dominated. But you see, they give the background index like that, but you refer to the tellurium 30 under 30 is close to 10 to the minus 1. It's not proven yet, but it's almost proven. They will finish the construction in the end of 2014 and will be commissioning in 2015. Another experiment is still at Gran Sasso, GERDA, that use germanium counters. In the first phase, those of either Moscow and of IJEX, that are both from INR, the Institute of Nuclear Research in Moscow. And this is the sensitivity, this is the lifetime, this is the Chapter claim, and this is the sensitivity as the function of exposure depending on the background index. Phase 1 aims for 10 to the minus 1 per kilo per keV per year, and this is the curve. So you can, in phase 1, go here, for example, with 15 kilo a year of exposure. That is already there. To exclude or to confirm the Chapter claim. So the design figure for the background was 10 to the minus 2. And we are almost there. We achieved 10 to the minus 2, 10 to the next phase will be to additional 20 kilos and go down to this value. And so we'll go between 100 and 150 millielectron volt. Now this is lifetime, but that corresponds to 120 millielectron volt. This is GERDA itself. Is made, the trick here is to have the germanium counters naked in liquid argon. Liquid argon and liquid nitrogen can be made very, very clean. So you avoid all the cryostat. The cryostat is far, so you absorb the radiation. The cryostat is stainless steel, rather pure stainless steel, with an internal lining of copper. Outside you have a water tank that absorbs the gammas and the neutrons from the radiation of the environment, and also an anticoincident for cosmic ray. This value of 2 10 to the minus 2 has been achieved compared with the one that was in the project. So the thing is rather well. The next, this is to show you some data. You see, in the experiment there are also some non-enriched counters, and this is the data, the blue ones. The red one is an enriched counters. You see, this is a logarithmic scale. You see here that is dominated by 2 beta, double beta decay. Here there is the argon 49 that is in the atmosphere, and this is the blinded region where the signal is expected, 40 keV around, and the background evaluated plus or minus 200 keV from here is 2 10 to the minus 2. The next phase will use a different type of detector that are broad energy detectors, where this is the configuration of the electrons. You have a pi plus contact here and this N, and this allows you to a better discrimination between the signal that deposit all the energy in a millimeter and a background that is mainly due to gammas that penetrate, make a Compton here, and then electron, and then another compton, and another compton, 2 or 3 of them, separated by a few centimeters. So you can distinguish from the pulse shape, you can distinguish the two. Another possibility that another candle we have a test facility, looking at the light, if made in the scintillation light of the argon, you can have an active anti-coincidence, and this is what you gain from here to the yellow. So you can gain at least a factor of 10. Here you see that might be 2 orders of magnitude, but conservatively we can assume that you gain a factor of 10. So in this case, you see with this new, I think it's more or less proven that 10 to the minus 3 can be achieved. If 10 can be achieved, as the background index 2 instead of 1 will run, GERDA will run till not 15 but 20 kilogram year, that will be next spring, and then will be open and go to so the data will be released, in the spring. And then you go to the next phase, and this is what you can gain. You can go to 10 to the 26 year. Now, the other one, NEMO. This again, this is an experiment that was done in Modena that was called NEMO 3, with different. They have foils of the isotopes. And on the two sides, they have tracking chambers that are Geiger chambers, so they may see the tracks. And then they have a small scintillator to measure the energy. So then the resolution is not very good, 300 Kelvin. You see, this is the tail, the blue one is the tail of the double beta with 2 neutrinos. They have a beautiful data for the double beta with 2 neutrinos, but this is the signal you expect, that you see is very wide for the 0 neutrino one. The green is this is radon that you can read of. They got rid of it, and you see that the background index is not so bad, including the presence of the radon. So they can improve on this background index with SuperNEMO. SuperNEMO is this thing here, to which they are working. They will build modules like that, with big foils and the chambers on both sides. They have to reduce the background surface contamination to this level. They are working at Canfranc with a test with that from here to here, This is SuperNEMO, NEMO 3, and this is what you need to have for SuperNEMO. They are in good shape. They are making progress. The same will, if this is what is the sensitivity as a function of the mass. Of course, the thing costs a lot. 100 kilos will cost a lot of money, but 5 kilo cost, a model of 5 kilo costs 3 or 4 millions, so that you have to multiply by the 20. They will be sensitive around 100 million electron volt. And this is next. This is the idea of next. The basic idea is from David Nygren, that is the inventor of the TPC. CINO is magic. The Fano factor of CINO is very small. The fluctuation of the ionization charge is square root not of the number of the ions. The number of the ions multiplied on the root by the Fano factor. So the Fano factor is small, means the fluctuations are small. So you make your calculation, you can, this is a gas drift chamber with 10 bar pressure, 100 kilos enriched xenon. We have already the enriched xenon. The limit is around, no, I'm sorry, this is the liquid, I'm sorry. Cancel. This is EXO 200, this is a liquid TPC where you collect the charges in the liquid that is running, has already published in this WIP that is small depths, which means waste deposit for the DOE, and they have in a clean place near to the, not so near to the waste, this experiment. They collected the electrons. This is liquid TPC, so the energy resolution is not very good where it is, but the background is rather good. These are the scheme of the experiment. You have all the photomultiplier to see the tracks. Inside, of course, there are shields around it. And I go to this is the energy resolution. The energy resolution, you measure both the ionization and the light, and they are anticorrelated. So if you want to, because of when the free charge of ionization recombine, they make light. So if you measure those, and every point here, but they are anticorrelated. This is a calibration run, so you can see that from here you have a rather good energy resolution that is 4% at the energy where you have the signal. So these are the nice results of the experiment. They have a tracking information or some topological information to can distinguish between multiple scattering and single scattering, the background dominated, the signal dominated ones. Also they can, when they reconstruct the position of the events. So you can, from that you define a fiducial volume in the middle of the chamber without surfaces, so you can note the contribution of the radioactivity from the surfaces. That is good. But in the xenon, liquid xenon is self-shielding, so the external part will absorb the radiation. It's a self-shielding that is very expensive because it's a rich xenon that will cost of the order of $1 million per 100 kilos. So you are spending money to have the rich xenon as a shield. But you obtain good result with that. So this is the same thing at two different scales. Here is a range between 800 keV and 3000 keV, and this is the region around where the peak is expected. All these curves here is the data, and all this curve here is the background model. You make a model of your background, you calculate, and you see if it fits the data or not. It does. And this gray part is the double beta with two neutrinos that you see the here is dominating, and the background is sort of 10% of the total. So it's not very much related to the uncertainty of the background model is not affecting too much the systematic error of the lifetime. This lifetime is the first time that is measured. And this is the value. You see is 2 times 10 to the 21 years. Now, if you go to the most interesting place, that's where you expect the signal. This is the tail of this is where the background is more, multiple site, and here where the signal should be, single site, and this is the region of the signal. There is no event in the region of the signal, and 3 or 4 of them are expected, so they can put a good limit, also by fortune if you want, because there is no event with 3 or 4 expected. So this is the limit, that 1.6 at 10 to the 25 for 0 neutrino double beta decay years. So it's 20 to the 5 years. You see, unfortunately, it's for order of magnitude larger than the double beta decay. This is usual. Maybe that is more larger than that too. Now, this is an idea of Raju Raghavan. Many of you have known him, that unfortunately left us almost 1 year ago. This was one idea of him to dissolve in liquid scintillator xenon, but I discussed with him 1 year ago, or more than 1 year ago, this idea, if you assuming that boraxino were the place where to put. And boraxino is the cleanest experiment in the world. Kamland is much less clean. So we were always doubting that, Kamland is not, you remember Kamland was built also for the solar neutrinos, but they never reached that cleanliness. So the techniques is a rich xenon dissolved in liquid scintillator. They have a lot of xenon, 300 kilos, and the limit they obtained is 300, 600 million electron volt, and now they are trying to clean the thing. You have inside you have this is the balloon inside the liquid, where inside here you have liquid scintillator with xenon dissolving in it, and outside you have the shield, that is another scintillator without xenon in it. So here the shield is, because it is separated with surface, so you have a surface nearby, not too nearby, but rather nearby, but you don't lose too much of the useful xenon. On the other hand, they have to make a cut and to take only the central part. And they have also water outside, so they have, the shields are made of water, liquid scintillator, and inside you have your detector with photomultipliers looking in. This is the old structure of Kablan. So reconstructing, of course, from the light coming from the light photomultipliers, you can reconstruct the position of the event here, 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 within a few centimeters, and define the central volume where you are more safe from the background. This is the result. And you see, this is the tail, this is double beta decay with two neutrinos, very good signal. They have a lifetime that is very well consistent with the one of EXO. And here is the region of the signal. But in the region of the signal, you have a big contribution of the tail of the double beta, and more things that you don't understand. You have rather a shoulder or maybe a peak in the region of the signal, a little bit at higher energies. If that is due to some contaminant that were unforeseen, and they don't understand very well. They claim this is due to mainly to this green thing. This is the peak of where should be the signal. The main one is silver, where it is the yellow one is silver, this silver here, metastable, that they claim to come from the Fukushima thing. If I subtract what they are calculated background, I find these points, and this is the maximum signal that they might accept in the fit. The rest is background, so that with this they give a limit. But this limit is depending on the assumption they make on this background, so it's not very strong, I believe. In any case, the limit is similar to that of that of EXO. Yeah, these are some. This is snow plus. Snow plus is where snow was. They have changed. Snow was heavy water inside and the normal water outside, so it had to be suspended. Now they put liquid scintillator inside that's lighter than water, so you have to keep the balloon down with some ropes. They have installed in the base here some new anchor points and some ropes. Of course, these ropes must be extra clean. And they aim to put scintillator in that makes more light that the Cherenkov light in the water. And to do some solar, neutrino physics, maybe dark matter, and also double beta decay. Here up, here they are working. They put in this big detector you put water to when you have to check the photomultipliers, and you go with the boat and you check your photomultipliers. They have a poor energy resolution, so they choose an isotope with longer. Of course, if the lifetime with two neutrinos is longer, your problem goes a little bit down. However, they can have very large mass, and that's what they play. The trick here, the handle here, is to go brute force with a very large mass. But to choose a lifetime long lifetime, they go to the neodymium. And neodymium cannot be enriched with the normal means. You need the Russian, the normally enriched materials cannot do. You have to enrich it with laser, and there is a laser installation. There was a laser installation in France by the time of the Cold War. This laser is not working anymore, and they need a few millions euros to restore the thing. So I don't know when the neodymium might be available. Also, neodymium is usually radio dirty. So this is again a problem. A minor problem probably is that the neodymium is a very strange nucleus, so the matrix element is very difficult to calculate. The main problem is here, I think. This is what they expect. This is double beta decay that takes all, this is logarithmic scale, so 90% of the region of the signal is due to double beta decay with the neutrinos. So if they have a signal, this is a 500 kilo with a mass of 150 millielectron volts, you see this small shoulder. Okay, so we'll go to the last one. That is next. The idea of next is again with CINO, that is magic due to, I'm sorry, I was talking of this before, but the smallness of the final number still there. So if you make your calculation, you see that you can reach full width at maximum, even 5.5% at Q beta beta, provided you don't amplify the charges. Because if you do amplify the charges, then the fluctuation in the gain on the charge near to the wire, this fluctuation will kill you. So you have not to amplify the charges. So what you do, you have these TPCs, and you drift the electrons, and when you drift the electrons, you go to the wires, and here to the wire you amplify some, you accelerate the electrons with the field of the wires, and the electron will collide with the molecule of the gas, that is xenon again, and they will excite this molecule or atoms, and that becomes light. So you have amplification of the light, scintillation light. You have both light, and this, if you read out this light, is proportional without big fluctuations to the charge that arrives to the wires. This energy solution is in xenon is crucial because xenon has a rather high Q beta beta. So the contaminants that can give gammas to give background here are only 2 or 3. But you have one of them that is the bismuth 214 that you see is extremely near to the. So you have this bismuth contamination is very near to the Q beta beta. So you have to be able to distinguish the two. Of course, you have here you have the energy and you have the tracking. So with the tracking you can try to have the Hammer. Here is the I'm sorry, here I was explaining the energy, the fluctuation of the number of electron ion pair, that is the number of the sigma is the square root of the number of those multiplied by the Fano factor, and the Fano factor is 0.15 in the gas xenon. But for example, for exo, that is liquid, is up to 20. So you can gain a lot going to the gas in energy resolution. And here is the scintillator, proportional scintillator counter, the principle, you make the electrons by the ionization. You drift the electrons, you bring the electron near to the grid, where you have a big electric field, and you amplify you accelerate the electrons, but you don't amplify the charge, you don't ionize anymore, and you only produce light. Okay, now they had started to make some prototypes. They had 2 prototypes, one in Valencia and one in Berkeley, and here are the beautiful results with one at 600 keV, the calibration source, and another at 500 keV, and that shows that energy resolution extrapolated to the Q beta beta is better than 1%. So if that is conserved in the real experiment, that they are in business. Now this is one prototype. What is the trick here? To the topology, if you have 2 electrons, both of them, at the end of their range, they have the peak in energy deposition, the Bragg peak. So they have a big energy deposition at the end. So you have some spaghetti-like thing with two blobs at the two ends. This, of course, is simulated. Instead, if you have a single electron, this is not simulated, it's a real one, the color gives you the proportional to the charge, the positive charge, and you see that there is only one position, one of the two extremes that you know the direction. So distinguishing between the two topologies is a powerful means to reduce the background. Of course, the gas is not self-shielding like the liquid, so you lose that. But on the contrary, you gain because the probability to interact in the gas is less than the liquid, so it's more transparent. So you lose something, but you also gain a little bit, and you gain a lot with the topology. Now, this is the design of the chamber. This is the shielding that we are building now with lead shielding side. The chamber is stainless steel, selected stainless steel with copper inside. And the background will be suppressed. The main problem is the bismuth 214 that gives this 2400 keV, and the thallium that 26. These are the only two isotopes that have energy above the xenon double beta. We will select a single track confined within the active volume. The energy in the relation of interest that is 1% full visual resolution, and the partial pattern energy deposition. With this handle, they calculate with Monte Carlo, but you know, you are never sure, that the final background window should be around 8 10 to the minus 4, so below 10 to the minus 3. It's the only one that. Now, to conclude, the sensitivities, there is a nice review article recent by Gomez Cadenas and company, when they try to extrapolate the results within a range for each of the experiments. This was before EXO started, with the different value of the matrix elements and some hypotheses on the reliability on the background index. So you see here this what they expected with EXO from GERDA first phase. This is the Claptor claim. So to confirm or exclude Claptor, you need to go through the matrix elements. In all cases, but one, that is the germanium. If you measure with the germanium, you compare directly the time. So GERDA phase 1 will check Claptor completely. This is GERDA 1, sorry. This is Quora 0. Quora will start with a tower that's called Quora 0. It's starting now. This is Kamlan then, how they expected. The result is not here, it's here. And these are the other one. This is a small plus that you see is not very competitive. This is GERDA phase 2. This is Quora, when it was built. It will start in 2014. And this is next, that will start a couple of years later. This is Super NEMO. This is This is Super NEMO, yes, and this is demonstrator of Majorana. Is similar to GERDA, but not with a traditional, let's say, cryostats, but very clean, and they are building now. This is another plot by Andrea Giuliani that showed the point of view of the two basic parameters, the full width at maximum and the background index. What matters is how many counts you have from the background in a window that is proportional, equal to the energy resolution, twice the energy resolution, whatever. So your sensitivity, number of count per kilo year in your energy window, where you look for the signal, this is 1, this is 0,1, this is 0,01. The red dots are the already done experiments. You see they are around, the best one is around 0.1. with the good energy resolution and a decently low background index. So you are at this level. The next generation, Majorana, GERDA, phase 2, Lucifer is, I did not talk of Lucifer, an R&D for bolometers with seeing the light to avoid the background on the surfaces. This is next, and this is EXO 200. This EXO 200 was done, so this where next should be a little bit better, more or less like Lucifer and Majorana and GERDA 2. And then is what came along then was done when he prepared this plot, and based on the Monte Carlo they made, and this is where they come out. So you might be wrong. This is the position of NEMO 3, and SNOW Plus you see start already in a position that is not the best in the world. Just to conclude, a dimension is missing, this again Andrea Giuliani, that is the scalability. I mean, to go beyond 100 or 200 kilo is no point if you don't reduce the background index below 10 to the minus 3 per kilo per cat per year. And if you don't have an energy resolution of the order of few percent. But there are other reasons that you can scale more or less easily. The scalability itself, you have just to buy, to make a TPC with 10 times the xenon in it, you have to make it just twice as big. For germanium, you have to make many counters, many diodes, and that is a lot of work. And even more for bolometers that are smaller. A germanium counter typically is 2 kilo. A bolometer is much smaller, so they can be scaled, but not so easily. And for external sources like Super NEMO, it's extremely difficult to scale. Another parameter are the cost. 1 ton of germanium, enriched germanium, will cost around under $50,000 or euros. Plus, this is not the total cost of the experiment, of course, because you need the other things. The natural tellurium will cost around 30, and enriched xenon is 10 if you are able, okay, if you find a good deal. So you see that maybe xenon is one of the best chances, but we have to see how next will perform. If next perform well, even liquid xenon might go ahead to larger mass. So that's it, more or less the conclusion. Neutrinos are the most exclusive of the known particles that are not so known, by the way. Has always given unpredicted surprises, so we can predict that they give more. They, for the first time, open a window of physics beyond the standard model. By the way, that was more or less contemporary to the construction of the standard model, because the first calculation of John McCall and the measurement by Davis of the neutrino flux from the sun was 68. So, and that was the solar neutrino puzzle, non-accounted hidden effects. There was a discovery of the mass of neutrino was discovered several times. The 70 keV neutrinos were discovered. The square of the mass of neutrino was negative in the tritium beta decay. There was a lot of discovery of neutrino mass, all of them wrong. Also, that is why personally I'm careful on a few standard deviation effects. Neutrino may be the only known fermion to be completely neutral. We have to prove it. It may be very difficult to do that. The present generation of experiments should be able to explore the quasi-degenerate region in the mass spectrum. That means down to about 100 millielectron volt. Nobody can go below 100 millielectron volt of the present experiments. And for doing that, will require a major experimental effort and many years. Thank you.
Thank you very much. We have time for a few questions.
This is about CUORI. There are individual crystals, right? So is it possible to see in which crystal the energy is deposited, or do you just have an overall signal?
No, not every crystal independently.
Okay.
The bolometer, you have a temperature sensor on the top of in the face of the cube, and you take out the signal from there.
So there is no position sensitivity. You don't know if it's near the edge or in the middle, or?
No,
Oh.
but you know you can anti-coincide if you have a count in one crystal. A gamma, a Compton electron might go out of one crystal and go in another nearby. In the case you can do. But with a space resolution of 5 centimeters.
I see. Thank you.
In Germany we do have from the space the pulse shape analysis.
Just a comment that the R&D stage, there is also an effort going on in India. There's a group which is engaged in looking at it's called tinting.
Indeed. So it's in India.
Yeah, it uses tin. It's a tin bolometer.
Not indium.
No, not Indian. Tin.
Tin.
Yeah, and the R&D is going on.
With the technique of Raggio Raghavan, I guess, no? No? Dissolved in a liquid scintillator. The indium are bolometers.
Tin goes.
Tin.
Tin, not Indian.
Tin.
Tin bolometers.
Any other question?
The students, do you have questions? If there was no question, means that I was too fast, maybe.
Very clear.
Not very clear.
No, you were very clear. That's why no questions.
No, there are two options. You might be very clear or not at all.
Okay, let's thank the speaker again.